Hello everyone. In this video, I'm going to go over section 4.4, which is polynomial functions, roots, and reducibility. So a couple of announcements, just draft one feedback for draft one of your paper. Your peer feedback on that is due Wednesday night at midnight. And then I will also leave non-public feedback, hopefully on the same time frame. Test 2 also is next Monday. The practice test and the solutions are already posted. We're going to have some questions that are not proof questions on that test. So make sure that you look over that and make sure you see what kind of questions there are going to be and practice them. All right, so getting into the material here. Throughout this section, the ring R that we're talking about is going to be assumed to be commutative. So keep that in mind. So not necessarily working with fields all of the time, but at least with a commutative ring. So this is the section where we finally get to talk about polynomials as functions. Up to this point, we've only been looking at polynomials as just elements of a polynomial ring. They were basically just formulas, and we could add together the formulas or multiply them together, and then that was pretty much it. So in this section, we finally talk about polynomials as functions. So the first thing here to define is what is the function that is associated with a polynomial. So each polynomial f of x, which of course has this written form, each polynomial in R bracket x is associated with what we call a polynomial function. So this is a function f from the ring to the ring, where this is the same ring that the coefficients come from. So it's a function from that ring to that ring. And the values of that function are found just exactly like you would think they would be by just plugging into f of x for x. So just replacing the x with the ring element that you want to plug in, okay? And then we say that each f of x in R bracket x induces a polynomial function f from R to R. So let's look at some examples where we go ahead and do this. So here we're going to let f of x be 2x cubed plus x plus 1, and g of x is going to be x cubed plus 2x plus 1, and these are in Z3 bracket x. So the ring in question is Z3. Z3, of course, only has 3 elements, which are 0, 1, and 2. So I'd like for you guys to pause the video here and go ahead and try plugging in these 3 inputs into both f and g and see what you get. Okay, so assuming that you went ahead and did that, I will go ahead with the answers now. So let's see, when I plug in 0 to f, I think I'm getting 1. When I plug in 1, I'm getting, let's see, 2 plus 1 plus 1, that's 4. But then 4 reduces modulo 3 to 1. And then for 2, I'm getting, let's see, 2 times 8, 16 plus 2 plus 1, that's what, 19? And then modulo 3, that also reduces to 1. So I'm getting 1 for all 3 values there. And then for g, when I plug in 0, I'm getting 1. And when I plug in 1, I'm getting, let's see, 1 plus 2 plus 1 is 4, which is also 1. And then finally, let's see, 2 cubed is 8 plus 4 plus 1, so that's 12, 13, which again, mod 3 is 1. Okay, so interesting thing here is that these two functions, these two polynomials rather, induce the same function. So this is possible when you're in a finite field. You can have 2 different polynomials that induce the same function. I think this usually seems really weird to students because you guys are really used to thinking of the polynomial function and the polynomial formula as being almost the same thing, like there's no distinction between them. But here I really want you to see that f of x and g of x are 2 different polynomials, but they have the same function. And there's other formulas too that would also induce that function, like h of x equals 1. So the function is not the same as the polynomial. There can be lots of different polynomials that give us the same function. And an interesting question here might even be to ask, how many different functions are there from Z3 to Z3? And how many different polynomials are there in this Z3 polynomial ring? And then if you can manage to answer both of those, what conclusion can you draw from that? So I'd like for you guys to pause the video here and think about these 3 questions. How many different functions could there be from Z3 to Z3? So a function from Z3 to Z3, you have 3 possible inputs, you have 3 possible outputs. And then how many different polynomials are there? And what can you make of the comparison? So go ahead and pause and think about those questions. Okay, so assuming that you paused and thought about those, so to determine any function from Z3 to Z3, you only have to figure out where each input gets mapped to. You just have to say, where does 0 get mapped to? Where does 1 get mapped to? And where does 2 get mapped to? 2. So this is 3 decisions, and they each have 3 options. So you can map each of those to either 0, 1, or 2. You can map all of them to 0, all of them to 1, all of them to 2, map 0 to 0, 1 to 1, 2 to 2, you know, whatever. So 3 decisions with 3 options each. So 3 times 3 times 3 equals 27 possible ways to do that. So there's only 27 possible functions from Z3 to Z3. Not very many. On the other hand, how many different polynomials are there in Z3 bracket X? Infinitely many. So for example, you can have 1, x, x squared, x cubed. Those are all polynomials. Okay, x to the 4th. Just keep going. X to the 5th. Now, an interesting question might be, are there only countably infinitely many, or are there uncountably infinitely many? This is a bit of a hard question for you guys, because I think, actually, I don't think, well, maybe you guys have the ability to answer this question. I think it would be difficult for you to answer it. Maybe until you've had like real analysis or something. So something to think about. Put that under your pillow at night, maybe. You could try Cantor's diagonalization argument, I suppose, with some polynomials. Okay, so anyway, the point here is that there's only 27 different functions from Z3 to Z3, but there's infinitely many different polynomials in Z3 bracket X. So the conclusion here is just like most, there are tons of different polynomials that have that induce the same function. Okay, there's only 27 possible functions that these infinitely many polynomials could induce. All right, so examples like the one that we looked at up here are like really, really, really common. Okay, now a related question, what about an infinite field? So this example here kind of depended on the fact that we were doing these reductions mod 3 and getting back down to smaller numbers. But what if we had an infinite field? Could 2 different polynomials induce the same function? So I'd like you to pause the video and think about that for a minute. And now I'm not going to answer this right now, but we will answer it at the end of this video. So we'll come back to that. Put it in your pocket for now. Okay, so next topic I want to talk about is roots and remainders. So now that we've got polynomials as functions, we can start to talk about their roots or their zeros, which is mainly what you guys talked about a lot in like middle school and high school algebra, was trying to find these things. So an element A in the ring of the coefficients is called a root or a zero of the polynomial, if and only if, when you plug in A to the function, you get 0. So you guys are already familiar with this definition, I think. So you could say that most of algebra is about trying to solve equations, and trying to solve equations generally, no matter what form your equation starts out in, the general technique is to like try to make it look like a polynomial, try to use polynomial techniques. That's pretty much all we got. So this is a really important definition. And then we have a theorem that actually has its own name. There aren't that many of those in this textbook. So the remainder theorem says, for a field f and f of x in f bracket x and an element a in f, the remainder when f of x is divided by x minus a is f of a. So this is kind of interesting. When you do polynomial long division of a function by this linear factor x minus a, you actually get f of a. It's kind of surprising, but you'll see why it's the case when we look at it in a second. But just to do an example right here to confirm, or to like see what this theorem is saying, let's go ahead and find the remainder of this function when divided by x minus 2. Let's do it using long division, and then let's compare that to f of 2, and we'll see that they're actually the same. So I am going to attempt to do the long division on the screen here with my finger. We'll see how this goes. Okay, you know what? I decided to not risk doing this with my finger, so I'm going to type it. So here's the little division house. So we're dividing this thing by this thing. So we got to figure out what can I multiply x by to get 4x cubed. So to get 4x cubed, I'm going to multiply x by 4x squared. Okay, and now I'm going to multiply this part up here by this part over here, and I'm going to subtract that down here. Okay, so 4x squared times x minus 2 is going to be 4x cubed minus 8x squared. Okay, and now I'm subtracting that from the top part. All right, so the 4x cubes cancel out, and then I'm going to have 7x squared minus minus, so plus 8x squared, so 15x squared, and then I still have the minus 9 part. Okay, so now I want to multiply, I want to figure out for the next term, what do I need to multiply x minus 2 by to get the 15x squared part here. So I'm going to do 15x up here, and now I'm doing 15x times x minus 2, and I'm going to subtract that, so this will be 15x squared minus 30x, all being subtracted. Okay, and when I subtract, I get, let's see, 15x squareds cancel. So now I have, the leading term is going to be positive 30x, and I still have the minus 9. Okay, so now up here, what am I going to multiply x by to get 30x here? So obviously 30. Right, and then I'm multiplying by 30, oops, so that's 30x minus 60. Okay, and now subtracting, let's see, 30x is cancel, so minus 9 plus 60, so 60 minus 9 is 51. Okay, so we got 51 for the remainder, and we want to compare this to f of 2. So f of 2 would be 4 times 2 cubed, which is 8, plus 7 times 2 squared, which is 4, minus 9. Okay, so that's, 32 plus 28 minus 9. So, oh, looky there, we got 51 again. So just doing all this to confirm, like, yes, when you divide by... So one thing you can see when you do this is when you divide by a linear factor, you always have to get a remainder that is of a lesser degree. So you are going to get a constant remainder. And then you can confirm, at least in this case, that the constant is the same as the one that you get when you plug in f of 2. But let's look a little deeper and see, why is this theorem true? So actually, I think I might like you guys to stop, pause for a second and think about why this should be true. And your thoughts should focus around the quotient, or sorry, the division algorithm theorem for the remainder theorem. So thinking back to the division algorithm for remainder theorem, or sorry, for polynomials, misspoke. The division algorithm for polynomials, why would that imply the remainder theorem? And then I will go over the reasons with you. Okay, so assuming you gave that some thought, let's go over why the remainder theorem is true. So first of all, looking at the division algorithm for polynomials, it says that if we have any dividend, that's the thing being divided, f of x, and any divisor g of x in a polynomial ring where the coefficients are coming from a field, it says that we can find a quotient q of x and a remainder r of x in that same polynomial ring that satisfy this equation. So this is the same as the a equals bq plus r equation that we had for integers, but it's just polynomials. So f of x equals g of x times some quotient polynomial plus some remainder polynomial. And then furthermore, for the inequality part, we have that the degree of r of x is less than the degree of g of x, or r of x is just the zero polynomial. And the reason this is in its own separate little part is because zero polynomial is said to have no degree. It has undefined degree. So just looking at the division algorithm, hopefully you guys can agree that if we put in a linear divisor for g of x, the degree of r of x is going to have to be less than less than 1. So it would have to be 0 degree, or r of x has to be the zero polynomial. Either way, that means that r of x has to be a constant. Okay, it's either 0 or it's some other constant. All right, so once you get that r of x is a constant, then what you can do next is you can conclude that just looking at the two sides of this equation here, this is an equation of polynomials, so the formula on both sides has to be the same formula. And if I plug in a on the left and I plug in a on the right, I need to get the same value. Okay, so when I plug in a on the left, I get f of a. When I plug in a on the right, what do I get? I actually get a minus a times q of a plus r of a. A minus a is obviously 0. So what I'm left with is r of a. But remember, we said that the remainder is going to be just a constant. Okay, so that r of a is just whatever that constant r of x happened to actually be. All right, so hopefully this makes sense to you guys. And if not, then maybe pause and think about it for a bit longer. So there are some consequences that we get from the remainder theorem that are quite useful. And the first one is the factor theorem. So another named theorem, very exciting. So the factor theorem says for a field f, a in f is a root of f of x in f bracket x, if and only if x minus a is a factor of f of x. So this is a pretty strong step towards the fundamental theorem of algebra. You remember the fundamental theorem of algebra is that for complex polynomials with complex coefficients, you have exactly the same number of linear factors as you have the degree of the polynomial, but they may be complex numbers. The zeros may be complex numbers. Oh, right, and I guess, I mean, the correspondence between roots and factors, it's like so ingrained in us that I hardly even notice that this is saying something new. Like, yeah, of course roots go with factors. Like, factors give you roots. But we didn't actually have a theorem that said that up until this point. It's just something that we've been familiar with since, like, middle school. Yeah, so when you have a root of a function, that means that x minus the root is a factor of the function, and vice versa. If x minus a constant is a factor of the function, then that means that constant is a root of the function. So those two things are like go hand in hand with each other. So why is the factor theorem true? Or maybe a better question might be like, how does this follow from the remainder theorem? So maybe pause and ask yourself that for a second. Either why is it true, or does it follow from the remainder theorem that we just looked at? Okay, so assuming you paused and thought about that for a second, I mean, hopefully it's pretty clear that if you do have a factor of the form x minus a and you plug x equals a into the function, like, you're definitely going to get 0. So this part should imply this part, like, pretty clearly. Now, why should on the other hand, a being a root, why should that imply that x minus a is a factor? That is a little bit trickier to answer, I think. But remember, we have the remainder theorem that says, in this situation, when we have a field and we have the polynomial and the polynomial ring from the field, if we take the remainder when f of x is divided by x minus a, that needs to be equal to f of a. Okay, and so if a is a root, then that remainder is f of a is going to be 0, which would imply that x minus a exactly divides f of x. Okay, so the remainder after dividing f of x by x minus a would have to be 0, meaning that x minus a is a factor. All right, so that explains why this part right here implies this part right here. Okay, hopefully that makes sense to you guys, even though we didn't do like a full formal proof. That's the gist of the proof. So let's go ahead and look at an example of using the factor theorem to find all of the degree 1 factors of this polynomial right here. So you can take any polynomial you want, and if you're able to find all of the roots, those correspond to the degree 1 factors of this factors like this, x minus a. Right, so let's see if we can find them all. Now the easiest way to find roots, this is not the easy way for real numbers, but when you're in a finite field like Z7, the easiest way to find the roots is just plug in all the values of Z7 and see if any of them give you 0. Okay, so what we're going to do is just like plug in what is f of 0, what is f of 1, and so on. Okay, so what is f of 0? I think boop, 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 5. If I plug in 1, I get 1 plus 3 plus 1 plus 5. What is that, 9? So in Z7, that's, no, sorry, that's 10. Gosh, I'm recording this too late at night. Okay, so that in Z7 is 3, not 0. All right, let's keep going. So f of 2, if I plug that in, what am I getting? 16 plus 3 times 4 plus 2 plus 5. You guys can do this with a calculator. I'm going to pause and do it so you guys don't have to watch me. So just, I did a couple while the video was paused, so I did get 0 for 2. And then f of 3 was a little tricky. Just a little trick you guys can do if it's easier. When you're doing f of 4, if I replace 4 with something it's congruent to modulo 7, I can replace it by subtracting 7 and get f of negative 3. And that's just like slightly smaller to work with, so it's like slightly easier to work with. That is an option that you guys have if you ever feel like using it. Right. And then you can keep doing them like that. So like f of 5 is the same as f of negative 2. That's easier to simplify. Okay, so the only one that I got 0 for was f of 2. So the only linear factor that this polynomial would have is x minus 2. Okay, so we can conclude that f of x equals x minus 2 times some other polynomial. All right, so that's pretty much all I wanted to say about that theorem. It is also possible, I guess, that there could be more than one factor of this, like we could possibly have x minus 2 squared, but we can't have any other linear factors. So some consequences, some corollaries of the factor theorem are the following, and we can talk about why these should be implied. So the first one is 4.17. For a field f and a non-zero polynomial f of x in f bracket x of degree n, f of x has at most n roots in f. Okay, so let's pause here, pause the video on your end, and think about why this should be true. So I think for me this makes the most sense if I think about it from a standpoint of contradiction. So like if this part wasn't true, like if f of x had more than n roots, then it would have to have degree more than n. So basically this, it's not written in the form of an if-then, but it's implicitly this is an if-then statement for a field f and a non-zero polynomial f of x in f bracket x. You can rephrase this as if f of x has degree n, then f of x has at most n roots. So then thinking about the contrapositive version, if f of x has more than n roots, then f of x has more than degree n, or just not degree n. So if we think about the situation where if f of x had more than n roots, then f of x would have more than n linear factors, so it would have more than n degree. Greater degree than n. Right? Because you don't lose degree when you're multiplying together factors. Each linear factor has degree 1, and that doesn't get lost because there's no zero divisors. You can't multiply non-zero things together and have them cancel out and become 0. So whatever the the degree of those linear factors is, that adds up to the total degree of the product. There's some theorem or other that says that, although I forget which number it is. It's this one. The degree of the product is the same as the sum of the degrees. Right, nothing gets lost. Right, so each linear factor contributes degree 1 to the degree of the product. All right, and then when you add up all those linear factors, they each contribute degree 1, so the total, the complete product would have to have greater degree than n. Okay, I hope that makes sense. Let's look at the next one. So corollary 4.18, for a field f and little f of x in big F bracket x, with the degree of f of x greater than or equal to 2, so quadratic or higher, nonlinear. If f of x is irreducible in F bracket x, then f of x has no roots in F. So why should this be true? Pause the video and think about this for a minute. Okay, so assuming you paused, this is another one where I think you can explain it more easily if you tackle the contrapositive version. So look at it in the contrapositive version, which would be if f of x does have roots in F, then f of x would be reducible in F bracket x. And that's pretty obviously true, right? Like, if f of x had roots in F, then it would have linear factors, right? And so that would make it reducible. Like, that's the... Having factors of a lesser degree is exactly what it means to be reducible, because the linear factors would have lesser degree. Because we said it had degree greater than or equal to 2. So that will be factors of a lesser degree, and that's exactly what it means to be irreducible. Or sorry, to be reducible. Okay, again, it's too late. Too late at night for me to be doing this. Hopefully you're not watching it late at night either. Okay, so the next corollary, or second to last corollary, before an example, is 4.18. So for a field f and little f of x in F bracket x of degree 2 or 3, f of x is irreducible in F bracket x if and only if little f of x has no roots in F. This might seem like really similar to the last one, but the difference is the last one was an if-then, and this is an if and only if. So in the last one it was saying reducible implies no roots, but no roots doesn't necessarily imply irreducible. And the reason that it doesn't go backwards in this one, you can have no roots and still be reducible. You may just be reducible to like 2 smaller polynomials that themselves are irreducible, that don't have any roots. So like, for example, in, let me actually put a note about this here so I'm not just like saying a bunch of stuff that you're gonna forget about. Note that the converse is not true. For example, so f of x in, if we're doing the real numbers, could be x squared plus 1, x squared plus 2. So that's obviously not irreducible. It's reducible because I can factor it. It's factored right there. I factored it. But it doesn't have any roots in the real numbers because all of its roots are complex numbers. Okay, so this is reducible, but has no real roots. Okay, so the converse of this one is not true, but corollary 4.19 is saying that the converse is true if the degree is exactly 2 or 3. If you notice here, like the counterexample that I made for the converse was degree 4. It's because that's the smallest degree counterexample to the converse that I can actually make. And why is that? So pause for a minute and think about that. Okay, so this is maybe a little bit harder to think about, but clearly this part, being reducible, implies no roots, because we already had that from corollary 4.18, right? So the only part you really need to worry about justifying is, why is it that having no roots implies that you're irreducible when your degree is 2 or 3? And let me write this down so you guys can follow the logic a little more easily. Since we already have left part implies right part from corollary 4.18, we just need to show right part implies left part. In other words, we have to show or justify that f of x has no roots in f implies f of x is irreducible in f bracket x when the degree of f of x is 2 or 3. And so actually I think this is easier to do with the contrapositive as well. In other words, turn it around and instead show that f of x being reducible implies that f of x has roots in f. So it's easier to understand the contrapositive, which is, let me just paste it again. So this one is reducible, implies this one does have roots. Okay, so this is easier to justify because now suddenly you realize, oh yeah, if f of x has degree 2 or 3, then it being reducible, well, there's only so many things you can factor a degree 2 polynomial into. If you're insisting on factoring it into parts that have smaller degree, then it's only going to factor into 2 linear factors, right? And if it's degree 3 and you're insisting that you can factor it into factors with smaller degree, then yeah, you got to have either 3 linear factors, or you could have 1 degree 2 factor and 1 linear factor. But either way, you get a linear factor, right? So again, this is for when degree f of x is 2 or 3, which you can write like this. That's because if a quadratic or cubic polynomial can be factored into factors of smaller degree, then one of those factors has to be linear, which means it has a root. Okay, so basically that's the logic that's going on, and I think the logic makes more sense when you turn it around and break it up like this. So yeah, that is the last corollary before this example that I wanted to look at, and then we're going to come back to the question from the beginning. So let's look at roots of some different, well, actually this is the same polynomial, but we're looking at it in different polynomial rings and thinking about whether it is irreducible or not. Okay. So what are the roots of f of x equals x squared plus 3 in r bracket x? So we don't really have like a great algebraic way. Like there's nothing that we've learned in this class that tells us that that doesn't have any roots in the real numbers. It's actually from calculus or previous classes that we know that doesn't have any roots in the real numbers, basically because we know that x squared has to be greater than 0. And so x squared plus 3 has to be strictly greater than 0. It cannot be 0. This has no roots because we know for any real number x squared is greater than or equal to 0. So that means x squared plus 3 is strictly greater than 0. So it can't equal 0. All right, and so because it has no roots, that actually does tell us from this corollary 4.19 right here. Since we know that f of x has no roots in f, so this right part is true, that means the left part here is also true. That means the function is irreducible in f bracket x. Okay, so, and that again, that's because it's degree 2 or 3. So by corollary 4.19, because f is degree 2, we can conclude that f of x is irreducible in this R bracket x. Okay, now roots of x squared plus 3 in complex numbers. Actually, you can just solve this, like set it equal to 0 and solve it. Okay, so x squared plus 3 equals 0 implies, so just move the 3 to the other side, so x squared equals -3. And then take square root. And you get plus or minus solutions. So let's see. So we have square root of, oops, -3. And then what you do is, just to put it in the standard complex terms, you break this into, let me see if, actually I know the keyboard shortcut. Yep, there it is. So this is square root of 3 times, which one do I want to put first? I guess times square root of -1, like that. You can break up the product of 3 times -1. And then you replace the square root of -1 with I. I usually put I first so that I don't get confused and think that it's inside of the square root like that, because otherwise I'll start thinking it's inside there. Okay, so these are the solutions that you get in the complex numbers for x, and these are in fact the roots. And so what that means is that you can factor this into x minus each of them. So first I'll do x minus the positive one. There it is. And then x minus the negative one. So when we do x minus the -1 there, obviously that's going to become plus. And you guys can just verify yourselves that if you FOIL this all out, it'll give you x squared. The outer and the inner terms are going to cancel out. And then I times I is -1. Square root of 3 times square root of 3 is 3. So -3. And then you have this negative here. So it comes back to being +3. So you do get back this polynomial right here. Okay, so not irreducible. It is reducible. All right, and then lastly, what about in Z7? So how would you figure out what the roots of this function are in Z7 and whether it's irreducible or not? So the answer to that question is you just try all the numbers. Just try 0 through 6. Okay, try plugging them all in. So just try all the possible roots. Okay, so f of 0 is going to be 3. F of 1 is going to be, let's see, 4. So I didn't get any yet. F of 2 is going to be, let's see, 4 plus 3. Oh, that's 7. So that is 0. That's a root. All right, let's see if we can find more. F of 3 is going to be, let's see, 9 plus 3, 12, which is the same as 5. F of 4, 16, 17, 18, 19, that's 5. F of 5, 28. Oh, I think I found the other one. All right, and then I don't think there can be any more because that's already going to give us x minus 2 and x minus 5. But we could just go ahead and try the last one anyway. So 36 plus 3, 39, mod 7 is 4. Okay, so we got 2 and what was the other one? 5 are roots. So what we can conclude from that is that f of x equals some constant times x minus 2 times x minus 5. And I think in this case we don't need to actually like solve for what the constant is because this coefficient on x is 1, so it should just be 1. We can leave that part out. In general, in the future, you might have to try to solve for what the constant is. All right, so not irreducible. Okay, so for the very last thing, I wanted to go back to this question. So at the beginning, we saw that when you're working with a finite field, 2 different functions, or even 3 different functions, because we also had this one, can induce the exact same, 3 different polynomials can induce the same function. You see how easily I just try to refer to these as functions, as if this part right here was the function, but it's not. This is the polynomial, or the formula, which is just slightly different from the meaning of what the function is. The function is all about what you put in and what you get out. The polynomial is about what coefficients you put in front of what terms of x. So we found that it is possible to have two different polynomials give us the same function when we're working in a finite field. But we actually have this corollary 4.20 that tells us the same thing cannot happen in an infinite field. And that's basically the reason why you guys hadn't encountered that before, is because you're only used to working with real numbers and maybe complex numbers, which are infinite fields. So if we have two polynomials, f of x and g of x in f bracket x, and f is an infinite field, then they induce the same function from f to f if and only if they are actually the same polynomials, the same formulas in f bracket x. So in order to actually prove this, we needed all the tools that we went over in today's notes. So let's look at the concept of how you do this. So the basic idea is if you're trying to show that f and g are the same function, you want to think about the polynomial of f minus g and think about its zeros. So I'll go through this with you guys. So suppose we have f an infinite field and f of x and g of x are in f bracket x, and suppose that they induce the same function. So they're giving us the same values for every input in the field. Then we're going to try to show that f of x equals g of x. So basically what we're doing here is we're showing that the left part of the if and only if implies the right part. We don't actually need to show that the right part implies the left part because we already know that. If two polynomials are the same one, then they induce the same function. Like, that much is obvious, right? So we won't bother with that part. Right, so we're going to try to show in this situation that if they induce the same function, then they are the same formula. Okay, so what we're going to do strategically is we're going to define this function called the h function, and h is going to be f of x minus g of x. And then we think about what are the roots of h. Well, what can we plug in that will give us 0? Well, we said anything, right? So h of a is going to be f of a minus g of a. We said that's the same for all of the a's in f. So every single element in the field is a 0 of this h function. But that is kind of weird, right? So to have infinitely many roots, because we just went over this corollary 4.17 that says the number of roots is less than or equal to the degree, but we have an infinite number of roots. So how do you make sense of this? Corollary 4.17 says number of roots less than or equal to the degree, but but no polynomial has infinite degree. So how could infinity be less than or equal to a finite number? Well, the way you make sense of it is you look back at 4.17 and realize there's actually one polynomial that this corollary does not apply to. There's like this one little loophole, and that is given by this word right here. So the 0 polynomial is an exception to the rule. And if you think about it, that should make sense, right? Because for the 0 polynomial, everything is a root. You get 0 whenever you plug in anything. So come back here, we conclude that our h function must actually be the 0 polynomial. That's the only one that could have infinitely many roots, according to corollary 4.17. So if h of x is the 0 polynomial, what does that tell us? Well, remember, h of x was f of x minus g of x. If that's the 0 polynomial, then f of x is equal to g of x. So that is the logic there, basically coming from the idea that infinitely many roots implies you must be 0. And that is it for today's notes. So send me an email if you had any questions or confusion, and hope you enjoyed the eclipse.